thank you very much for the introduction. Thank you very much for the invitation. So I'm happy to be here. Today I'm going to talk about some results that we obtained. I included Constantin, who is a last year PhD student with me on the first slide, but this is also joint work with, especially the last part, other colleagues. Gilles Pagès, Eric Moulin, Edouard Oyalon participated to one of the projects. So I'm going to get directly into what I'm going to present. My goal is to talk a bit about some things that we may encounter in the federated learning regime, which is the regime. Okay, that's okay, I'm going to live with the echo too. Which is the regime of collaborative learning in which several, let's say, participants in a network want to learn jointly a model. So this could be applied to for example, the context of the previous talk, in which several hospitals may gather data sets, each of them having a few patients, only very few children, and may want to put together these statistical resources in order to learn the best model. But actually, there are plenty of constraints that can be applied on top of that. So I'm going to spend like a few minutes describing those constraints and describing how basically we want to tackle those from the optimization and statistical point of view afterwards. Afterwards, I'm going to, basically introduce 2 or 3 main ideas on compression and stochastic gradient descent and stochastic algorithms more generally. So there are going to be 3 main parts in the rest of the paper, and together with some algorithmic and convergence results. Okay, so this is mostly statistics and optimization together. That's what I've been doing for now a few years. So the topic is mostly in between stats and optim. Okay, so a few words on federated learning. So a very schematic representation of what I've described before with the hospitals. I have a central server, so this is my central node. Okay, so that doesn't work either. Let me double check if maybe I can get the pointer. Okay, I can't get that. So I have a central server, here it is, okay, that communicates with multiple individual entities. So these entities could be, each hospital is an entity. Each of those entities holds data sets, and the central server wants to build a model. And obviously, the central server wants to improve the model by having multiple communications with each of the individual agents. And what are the constraints that we want to add on top of that? So the first one is heterogeneity of the data sets is a problem. So typically the distribution of each data set is not the same. This was also the case, something mentioned in the previous presentation. So we could have that one hospital has very young children, let's say age 0 to 10, and another hospital has older patients like 10 to 18, and maybe the other one has even older patients, adults, like age 20 to 99. And this means that the models that would be ideal for each of the patients may not be the same. And one way to tackle that would be transfer learning, as it was mentioned in the previous presentation. So we learn a model on the one data set on which we have many observations. This would be the adults. And then we try to transfer it and fine-tune it, let's say, on the other data set on which we have very few observations. And in the federated learning framework, the personalization is one of the challenges, so trying to adapt the models to everyone. But we think of data sets that are not like just one big one and one very small one, so it's not exactly transfer learning. It's more, let's try to learn all together something such that we all benefit from as much statistical power as possible. Okay, so heterogeneity, adaptation to the different data sets have been mentioned. The third one, which is one of the most important one of the ones I'm not going to talk about today, is privacy. So again, the hospital context is perfect for that, because we don't actually want to share the data, because the images, the radius may be completely private, and it would not be possible to share that with any third party, in fact, with today's constraints and regulations, and that's for the best. And so we have to be able to exchange information without actually exchanging private information, which is obviously something very hard to do. And finally, communication, which is the point I'm going to talk the most about today, which is probably not the best example for the hospital data set, although some medical data may be very heavy. The context I'm thinking about here is more like, let's try to train a language model. You have heard about those language models recently because they have been in the news a lot. And those language models could be trained by having a network of phones, let's say 10 billion phones in the world, all participate in the training. I'm not saying this is desirable. Okay, I'm saying could be one application. And that means that each of the 10 million agents here are going to recursively exchange updates on the model. And you know the size of those models is critical. We have heard about, like last week, models being only, I think, 90 billion parameters. So only around 100 gigabytes of data to store the model. Obviously, that means that if the model has such a size, the gradients of a loss which would be computed on that model would have the same size, which means that what I'm going to do afterwards, which is exchanging gradients iteratively, would not be something super practical. So I mean, we don't at least I don't feel like downloading 10 gigabytes of data and uploading very noisy random gradients of the loss on some of the observations on that very large model back to a server every day. Okay, that's completely out of what we can imagine doing. Okay, so these are like three of the main high-level challenges. What it corresponds to on the mathematical side is doing statistics, optimization, and algorithms. So I'm trying to see how we can actually tackle those constraints while preserving as much statistical power and having algorithms that run in an efficient way. So this is what I'm going to do. Very briefly, I just want to, I'm going to show the entire slide because the slides move a lot when I change. Just 1 minute to say what I think is currently going on in the federated learning community and more generally decentralized learning community, where we're at and what we want to achieve. So where we're at is that I think there are many problems that are currently tackled. I mean that I think before a few years, before 10 years maybe, those problems will be solved. This is how to design algorithms that face those constraints, and how to, basically implement that in practice and have a fair evaluation of those models, including on actual medical data sets. So people have been working on having things that actually work in practice, not just toy models, as I'm going to be doing in the talk. Obviously, the case of decentralized learning, which is learning but not communicating all of us with a central entity. I could name Sylvain as the central entity, and we're all communicating with him. But we could also decide that we're all going to communicate only with our neighbor. Maybe we don't trust Sylvain. I do trust Sylvain, though, but maybe we don't. And so there is a network now of communications, and so it needs to be tackled in a different way. And personalization also is something that's tackled. And things that are much further, and perhaps one of the most important aspects are regulation, having strategic agent, meaning that maybe Sylvain wants to betray over all of us, and maybe Sylvain has no interesting data on his phone, I don't know, but just wants to benefit from our model. Sorry, Sylvain, I'm taking you as an example. I hope you don't mind. And also having very large models in the decentralized fashion is also things that are up in the future. Okay, so let's move towards the mathematical framework. Again, I'm going to show the slide entirely just to have as least moving around as possible. So what we want to do mathematically is solve such a problem. This is minimizing a function f of w. This function f of w being expressed as the average of over n agents. So n here corresponds to the number of agents in my graph. So this would be the number of persons in the room if each of u is an agent. And each agent holds what we call his local loss. So this is fi of w. Maybe I should zoom in a little bit. At least this is. Okay, this is fi of w. This is the local loss that can be expressed. Again, maybe I should have said that before, but we're in this supervised machine learning framework in which we want, let's say, to do prediction. So each of us observes inputs, wants to predict an output. Okay, this is the classical supervised machine learning framework. And to find the best model w that want to optimize upon, what we're going to do is define a loss function, which is L. And you are not going to see L in the future. I'm going to hide everything under the rug afterwards. But my function L here measures the difference between my prediction W on the inputs and my output. And Z is just my data point. And you see that what makes the dependency on Fi of W, my local loss, the only thing that changes between two different agents is the data distribution Di here. So I assume that the distribution of the data points that I observe is not necessarily the same on all agents. Okay, again, in the hospital case, this would be that D1 is the distributions of the observations for very young patients. D2 would be the distribution of observations for patients aged 10 to 20, etc., etc. So there is a difference in the distributions here, and we're going to see how this actually impacts the convergence of the algorithms afterwards. And okay, how do I do that, and how do we do that today in machine learning, just the supervised machine learning framework? Typically, we have very large models. D is extremely large. We have extremely large number of observations. N is extremely large. So we are going to be looking for algorithms to optimize this function, or let's say first any of these functions, iteratively, that have a very low complexity. Low complexity with respect to N and low complexity with respect to D. And so the one solution that has emerged the most is stochastic approximation, mostly known, I guess, for most of you as stochastic gradient descent. That's how we train deep neural networks. And the reason why we use this algorithm is because we use typically first order gradient information, which is linear with D and doesn't involve any like higher order information on the function. And we use stochastic information, meaning that we don't use all the points at every iteration, but only very few of those. Okay? So again, this is to tackle both the complexity with respect to D, the dimensionality of the model, and the complexity with respect to N, the number of observations that we have. So we're going to do a lot of stochastic approximation, and what does that mean in practice? That means that we have a function here that we want to optimize on the central server, which is finding the best model that performs on average the best on the average of all losses. I'm not doing any kind of personalization yet for the moment. Won't be doing personalization today. I'm just trying to find a model that performs well enough on the average of all data. And to do that, I'm going to communicate iteratively with each of the agents. Each of the agents holds its own dataset. Okay? Any questions up to now on that framework? I think I have defined everything. I'm just going to go through that to check that. So Fi is the global cost function. Fi is the local loss. N is the number of workers. D is the dimensionality of my model. W my model. Di my local data distribution. And the only thing I haven't mentioned yet is that I'm going to assume that at each step I can observe gki, which is a stochastic oracle on the gradient of the function fi. Okay, how do I get that in machine learning? What I do is I sample a few points, maybe points I have never seen before if I really have access to a large data set. Sample a few points that I have never seen, and I take the gradient of the loss L here at the model W, loss observed only on these few points. And that gives me this stochastic oracle, and you're going to see afterwards that I'm going to assume that gives me a stochastic oracle which is actually unbiased, and I'm going to make assumptions on this oracle. Great. So let's wrap up already. The first time I want to solve this problem here, I could just do what we call distributed optimization. Distributed optimization would actually correspond to doing something like that. Okay, so distributed gradient descent or distributed stochastic gradient descent would look like that. At each step, I would update my model WK from WK minus 1 by doing what we do, a stochastic gradient update. So I move with the step size gamma in the opposite direction of a gradient or stochastic gradient of the loss. And the stochastic gradient of the loss FW is expressed as the average of the stochastic gradients of all the functions fi. Okay, so this is just actually what I've written here is exactly stochastic gradient descent. And the only particular thing is that because my function is expressed as an average of n clients, my stochastic gradient is expressed as an average of n clients. And so to analyze this algorithm here, I would actually, not even have to do any particular things related to the federated or distributed case. This is actually what we were analyzing in if you have seen a lecture on stochastic gradient descent, you have analyzed this algorithm just without the 1 over n and n, but that doesn't change anything in terms of properties. So this is very easy. Now, as we've said, one thing that is central in my talk, and which is actually central in federated learning and other applications, is this communication constraint. I cannot allow myself to just communicate at each iteration a gradient or stochastic gradient on all clients. So what I'm going to do, and there are going to be two different approaches, is, come on, that's, okay, I'm going to do that like that. Oops, perfect. What I'm going to do is one or two things. The first one would be compression. That's what I'm going to talk about today. So in compression, you have to hear compression as something that you do whenever you have a file and you want to reduce the size of the file. I'm going to take any information that I exchange, gki, and pass it through a filter that kills most of its size. So basically, you can imagine a vector. I'm going to give more details afterwards. And for any element of that vector, which is 32 bits to store, you just keep 1 bit. You keep the sign, let's say. And that means that instead of transmitting 32 times d bits, you are only going to transmit d bits to transmit such a gradient. And maybe even more than that. Well, we're going to be very drastic on the compression that we use. This would be compressed distributed stochastic gradient descent. And this is one algorithm that I'm going to study a lot today. I'm going to explain why this is not so trivial to analyze. And the second one, which is, in fact, maybe the most popular today, but basically these two behave in very similar ways, is to do local iterations. So it says, I transmit my model to Gilles now, and Gilles is making many, many iterations on his own phone to optimize a lot the model before transmitting back the information to the central server. Okay, so that means that here, instead of performing one iteration, I'm going to perform many iterations. I'm going to explain how these two things actually interact with the heterogeneity that I've talked about at the beginning. Okay, so one word on compression. I promised that a minute ago. So what we mean by compression is we consider this vector. Maybe let me again rewrite that directly. So I have my vector, which is d-dimensional. Here d equals 6, but in practice d equals 50 billions. It's much more problematic. And I'm going to, instead of transmitting that, I'm going to transmit a vector which has only weights 0 and 1. So here I would have 32 times d. Let's say all of those are integers. It's not 1, it's 1.112, I don't know, pi. And here I'm just going to transmit a vector of 0 and 1s. Okay? And how do we do that? I mean, it's a very old signal processing problem to find a good way of basically transforming a vector into something which has only a few bits per coordinate. And what we're going to do is something like that. So I'm going to consider, let's say, the two first coordinates. So this is v1, v2, right? And I'm going to project each of those coordinates on the axis. So here I have first rescaled the vector, let's say, to be, let's say, in the unit ball. Here it's the infinity unit ball, but let's say any unit ball. All coordinates are just between 0 and 1. I project the coordinates so that the coordinates are, now that this is maybe 0.2. And afterwards, I'm going to just randomly sample a number, a Bernoulli with parameter 0.2. Okay, so this would be just a Bernoulli of parameter v1 divided by norm of v. And same for the other coordinates. Okay, and doing that, I mean, basically, I'm going to output just a 0 or 1 for each coordinate. Okay, this is very drastic, and maybe a very simple question, and a naive thing that we do is just say, okay, I have a grid now with 4 different points, and I just take the nearest neighbor in the grid. That would be, that would normally be what we call Voronoi quantization, and that would be the simplest approach, in fact, to performing quantization. The reason why we're rather going to rely on stochastic quantization, meaning that here my output is going to be a random variable, is because we want to, I will come back to that, but we accept that we have a lot of randomness, but we want to preserve the average of the signal. So just like stochastic gradient descents or stochastic gradients are enough to learn a model, we are very happy to have stochastic estimates of our gradients as long as the average points in the correct direction. So this kind of stochastic quantization is really going to be the thing we rely on. Okay, so that's the first way to transform, let's say, a vector v into a vector that has only 0 and 1 coordinates. This is the quantization scheme, and this was proposed, I mean, this dates back to the 70s in signal processing, or even probably before. In machine learning, this was reintroduced in like the 2015s. The second way of performing quantization is what we call sparsification or projection-based. It is saying I take my vector and I only transmit the first 2 coordinates or any 2 coordinates of my 6-dimensional vector. Okay, so there are several ways of projecting. We could say I keep just a random subset of h coordinates out of d. That's what I've just described. Or we could say I keep each coordinates with probability p. So I sample a vector of Bernoullis with probability p independence, and I keep each coordinate with that probability. Or I could say I transmit entirely my vector with probability p, and I don't transmit anything with probability 1 minus p. Okay, and if we think about these 3 things, they're exactly the same things. The only thing that I change is I take my vector, I multiply it by a vector for which each coordinate is random, each coordinate is marginally a Bernoulli with parameter p, and the only thing I've changed from between these 3 schemes is to change the correlations between my Bernoullis in the vector that I multiply by. And interestingly, all those schemes are going to be analyzed in exactly, I mean, so this is that comes just next, we're going to make one assumption that's going to describe the behavior of our quantization scheme. And afterwards, our quantization scheme is going to be hidden under the rug. We're just going to assume that we have this quantization scheme that satisfies these two properties. The expectation of my compression of any vector delta is delta, which I could achieve before by saying that for each coordinate with, let's say, a coordinate v1, I was sampling a Bernoulli with parameter v1. Obviously, I keep the expectation. And the variance is bounded. Okay, the variance c delta minus delta is bounded proportionally to a constant omega. It's going to describe how hard my compression is, how powerful my compression is. The larger omega, the less coordinates typically I transmit. And proportionally to delta squared, the square norm of the variance. The square norm of the gradient of the vector that I compress. And why is that constant appearing here? I mean, basically because for any linear or projection-based method, I mean, x and the norm of x appears as scaling. So obviously, in only of those cases, these are linear methods. So the variance would scale as the vector. And in quantization-based methods that I've shown before, the first thing I was doing, as I said, is rescaling the vector to be in the unit ball. So afterwards, after transmitting, and I'm going to rescale back. And so I'm always going to have something that scales with the vector here. And why is that helpful? It's helpful because, again, I'm going to apply that to stochastic gradient methods that are like more generally gradient methods. And my hope is that as I converge, I'm going to converge towards a point at which my gradient is close to 0. So my compression errors are going to be very small to 0, very close to 0 too. Okay. Okay. When did I start? What's the timing, more or less? Never mind. Yeah, you have like 15 minutes. 15 minutes. OK, that's good enough. So there are three things I want now to show you about those compression schemes. So what I'm going to do is do this, what I've described, exchanging iteratively information. That's OK. That's OK. Tell me when I have no more time left. So I'm going to exchange iteratively information. And what I want to do is to pass every information that I exchange through one of these compression schemes. And I'm going to be drastic. I'm going to decide that I'm compressing information in both directions, both when the server talks to the workers, that's me talking to all of you, and maybe when the workers talk to the server, that's me. Okay, so information compressed in both directions. And the first the three things that can be done is trying to understand how this impacts convergence. Especially, I'm going to discuss a lot how mitigating the impact of heterogeneity and compression can be done. So this is my first point. I'm going to give a lot of details. And afterwards, I'm going to talk about feedback loops and maybe designing schemes based on Voronoi quantization. OK, so how to reduce the communication cost? I want to explain why compression or local iterations, these two methods that we've talked about, why those interact non-trivially with heterogeneity. And so there are two ways, as we said before, of reducing the communication cost: making many local iterations, that's what Gilles was doing, or compressing the signal that I transmit. That's what I will be talking the most about. And for the two situations, what we're going to see is that actually this is problematic. So let's have a look at this situation. So W star is the point I want to reach. This is my optimal model. And as I've said, I have heterogeneity, meaning that each client holds a function which is different. And that means that the minimum of each function is actually different. So maybe I hold the function, someone holds the function f1 with minimum w1 star, someone holds the function w2 star, and someone holds the function w3 star. So f3 that has minimum w3 star. And if I do too many local iterations, this is just like trying to make a group project when no one talks to each other, and each people converges to its own local optima, and afterwards trying to average those minima together is clearly not going to obtain the global optima. Okay, so this is saying there is absolutely no reason that W star, the optimal point for the average function, is the average of the optimal points of each function. I mean, it's like absolutely no reason that it holds, which means that if we do too many local iterations, we're actually not going to converge towards the correct point. That's the first point of view. It's called client drift, and this is what applies for local iterations. The related thing is, in the case of compression, is phrased in that way. I'm going to converge towards W star, at which the gradient of the average function is going to be 0, Let's say my function is smooth, and let's say my point is in the interior of the domain. So my gradients, my sum of all gradients f1 plus f2 plus f3 at w star is going to be 0. But clearly, none of the function f1 star, f2 star, and f3 star is happy at w star. So all the gradients are actually non-zero for the local functions. And that means that when I reach w star, I actually have an equilibrium point for the average function, but not an equilibrium point for any of the functions f1 star to f3 star. f1 to f3, sorry. So how to fix that? Why is that a problem? First, because one scheme of compression that I've given you, and I've said all those schemes basically are in some sense equivalent to each other, is saying with probability p I transmit my vector, and with probability 1 minus p I don't say anything. And if we do that all together, let's say there are like 40 people in the room, it means that I ask a question to all of you, and most of you, let's say 90% of you, don't transmit anything. And the 10% of you, that's 4 of you, transmit me the complete vector. Okay? And in the drastic case with 3 participants, that means that basically I'm not going to receive these 2 vectors. I'm only going to receive this 1 vector. Okay? Which means that this partial participation of the participants means that even if I've reached W star, because of the heterogeneity, I'm not going to stay at W star. Okay? So again, let me just summarize that. We have 2 ways of tackling communication constraints, local iterations or compression. And in both situations, we have a problematic behavior because of heterogeneity, because all the functions actually want to go to different points. Okay? So this is maybe the first idea that I would like you to remember or to understand, this trade-off between heterogeneity and communication constraints. Either way we try to fix it, we run into another problem. So how do we actually fix that? So let's again have a look at the algorithm. I'm going to first quantify mathematically what I mean by that. So this is my algorithm. This is going to be the set of assumptions that I make. So I have 3 assumptions. I'm looking at this algorithm that compresses the gradients sent from the local workers to the central server by C up, averages everything out on the central server, and compresses it back before sending it back to the central, to all the workers. This is the algorithm I have been talking about from the beginning, but now with this double compression scheme. And so my assumptions are that my compression scheme satisfies this unbiased with relatively bounded variance assumption that I have written before. So this is valid for all the schemes I have described. That my stochastic gradients have bounded variance. So this is the assumption that was in all your lectures on stochastic gradient descent. And now something that describes this heterogeneity that we have between the clients. I'm going to say that the gradient of the function fi at the global point is gradient that was non-zero. You remember on the previous graph. Those gradients are all bounded by a constant b squared. This is not actually an assumption. This is just like saying I define a constant b squared that describes the heterogeneity. If b squared equals 0, it doesn't mean that all the functions are the same. That means that all the functions have the same minimum. And this is going to be good enough. And now if I look at that, and actually I'm just quantifying what I've said before, if I look at the compression of my average compressed gradients, this update that I make, it's actually kind of, shouldn't even be a lemma, it's a computation. This is an unbiased oracle of the gradients, because without any compressions, it's an unbiased oracle of the gradients, and my compressions are unbiased. So obviously, I cannot create any bias by applying unbiased schemes. And I have a variance, which increases in the following way. So basically, each operator tends to multiply the variance by a constant omega up, then omega down. And here, because I have an averaging scheme, what I have is 1 plus omega down times 1 plus omega up divided by n. So omega up quantifies the compression for the uplink compression. Omega down quantifies the compression for the downlink compression. And so I have this multiplicative thing and this reduction with respect to the number of workers. So this is the first part. And if I only had that, I would be kind of, in some sense, happy. I've reduced a lot the number of bits, but I have increased the variance. Maybe that's fair. Maybe we see how to tackle that afterwards. The problematic part is this one. The problematic part is that even if I have pure gradients, I mean deterministic gradients of all functions, so sigma squared is 0, almost surely everywhere, and I have a residual term here which is proportional to the multiplication of omega down and omega up again, and that depends on the heterogeneity. Okay, and this term comes exactly before, because what I've described before, if I consider compressed deterministic gradient descent, as before, with this partial perturbation scheme, I know that I have some variance. I know I'm actually not converging towards the optimal point. So I know I cannot really escape that. It's just, I mean, basically, this lemma is exactly a mathematical quantification of what we see on that image. Okay, and this is a tree-line computation. It's actually not something difficult at all. Okay, so this is our main problem. And this term actually doesn't really matter. I just wrote it because it's needed mathematically. But anything that scales with the gradient is actually going to vanish asymptotically. So how to fix that? Our objective is now to fix the algorithm in order to recover the convergence of the homogeneous case, meaning having something that doesn't depend on b square. And the way this is done is to say, I'm going to perform my algorithm, but also learn variables that are meant to correct my gradient. So I'm going to call that a memory term. I'm going to learn iteratively a variant that converges towards this gradient of fi at w star. So I'm learning my correction vectors. And instead of compressing my gradient, stochastic gradient, I compress the difference with that memory and add back the memory afterwards. Okay. What that corresponds to in the optimization landscape is to say, I had actually different functions. I'm going to learn a linear correction on all functions, such that all the minimum actually correspond. Okay, so I had f1, f2, f3. I'm going to learn linear corrections that have all the optimums actually merge at the end. Okay, and obviously, if I'm able to subtract this gradient of fi at w star to any stochastic gradients, if I looked at the gradient of g of fi minus the gradient of fi at w star times omega, okay, this function, the function, my linear correction is having fi minus the gradient of fi at w star times w. Okay, this is why I say it's linear, because I just had the linear term, and that means I'm subtracting the gradient of fi at w star at any gradients of fi. And actually, if I look at the gradient of this changed function at w star, it's obviously now 0. Okay, so this is actually a powerful scheme, and what we can show, I'm not going to go into the details of the algorithm, is that when we look at the convergence, we have basically, I look at my iterates compared to w star in terms of average square distance. I have a linear contraction depending on the initial term. This is very much like any stochastic gradient descent algorithm that you may encounter. And what I'm going to look at more precisely is this variance term that I have on the right. Okay? And this variance term that I have on the right, if I don't use any correction here, so I don't use hki, I have exactly what I had before. So the problematic term that was depending on b squared, this is problematic, while instead, if I use the correction, I'm going to have something that doesn't depend on b squared anymore. Okay, so what I'm saying here is that if we learn those variables correctly, we're actually going to be able to just like drop the impact of heterogeneity. Okay, and I don't know how many experts there are in the room about stochastic algorithms, but this is very related to variance reduction methods in which I actually try to find those linear corrections that help me reduce the variance of the method. Okay, so this is the first summary of the first part. I have this heterogeneity and compression interaction, which is problematic. My convergence is impacted by the heterogeneity if you run the algorithms, and if you actually run either local iterations or with compression, whenever you have this heterogeneity, you fail to converge efficiently. And those methods that rely on like, oops, sorry, the references are missing here. So there's a small bug in the compilation. I'll fix that if the slides are uploaded somewhere. So there is the uplink memory that we have added allows to basically recover limit variance, which is the same as without heterogeneity. And this is a client-wise variance reduction scheme, and this can be applied to many different regimes, especially to Langevin algorithms, EM algorithms. I mean, basically any distributed algorithm that you may encounter requires this kind of scheme to face heterogeneity. And I mean, in each case, it's not applied in exactly the same. And maybe we have to do more work. But this is out of the scope of today. OK, second point. Am I being too fast? OK, I hope so. Hope not so. Second point is section B. This is this one. OK? I want to mitigate now the impact of compression by feedback loops. And this is somehow orthogonal idea to what I've presented before. But an idea which is kind of very nice and very simple at the beginning. How does that work? OK, so let's say I do compression. And typically, in some sense, what we do compression, we may have the feeling that we're just having more noise on our stochastic oracle. I had stochastic oracle, I compress it. I have another stochastic oracle with even more noise, and maybe this even more noise depends on the heterogeneity. That's what I've described. But there's actually something on top of that. What I actually do is I receive a stochastic gradient with some noise, I compress it, and I pass it to Sylvain. But meaning that I have actually observed a stochastic gradient, and I have observed the compression, and maybe I could, before passing that to Sylvain, the compression, I could remember and store the difference. This would actually be something useful because in some sense, I meant that I have transmitted partial information to Sylvain, and I could keep whatever it remains and add it in the future into what I try to transmit. Okay, so this is what we call error feedback, or basically feedback loops here. And in the case that I've described before, this like double compression scheme, the way it can be phrased is it's exactly the same idea you're going to see, but in a slightly different regime, is to say, what do I do? Okay, I receive stochastic gradient. Each agent measures stochastic gradients. It compresses it. It sends basically sends the message to central server that aggregates, does compression, and then sends that back. And so the good news with that is that actually all the local workers have the same support points for those gradients as the model of the central server, WK. So this is fair. The bad news is that in some sense, you all transmitted in me some information that was compressed, you averaged that, and then instead of using that information, I first passed it through a filter that degrades that information, and then I used it, and then I transmitted it back. So what we would like to do instead is something like that. I would like to say, okay, you transmit me your information, I use it, so I update my model with WK-1 and all the information you have transmitted, and then I send you another model, and maybe a bad one, okay, one which is degraded, maybe you have a very poor update, but at least I have used all the information, and then you are going to send me back gradients, but gradients at random points, and those random points are not going to be the same point as the model I hold. Okay, so now what I decide is that I'm going to use all the information you provide me, but I'm going to send back a random model to each of you, and you are going to measure gradients at this random model. And that means that if I do that, at least I have used the information, but you are going to measure the gradients at the point w hat k. And what I'm going to try to enforce on the w hat k is that, I mean, first, the w hat k, you could compute it by information that was compressed. I still want to compress information that I send to you. Then the average of this stochastic model has to be the correct model. So I want that you all measure gradients at random points, but around the correct one that I hold. And obviously, I want the variance to be controlled. Okay, so how do we do that in practice? I mean, for the moment, I've described the scheme, which looks kind of nice. I haven't said exactly how I'm going to compute w hat k, and does that actually work in practice? So there are several attempts that could be made. Maybe I'm not going to go through all of those. The simpler thing could be to say, okay, I do model compression. So same update line as the first line, my three conditions that I want to satisfy, and maybe I take my model and I compress it. But you have to think of compression as maybe taking, let's say, 10% of the coordinates. So I'm having like 50 billion parameters, and I'm send you only like 1/10 of those. This is not going to be good in terms of variance. The variance is not going to go to 0. Another thing that I could do is say, okay, I take the model that you hold. I know this model, this w hat k minus 1. And I'm just compressing the difference between what I have, now wk, and w hat k minus 1. This sounds like the best solution in some sense. I know where you are at. I know what I have. I take the difference. I compress that. Because my compressor is unbiased, I'm keeping the average of the true model. But actually, that doesn't work either, because the compression schemes that we use tend to add more and more variance as we go on. So maybe I don't want to go into too much details. Maybe it's enough of a teaser like that. We actually need to use what we call a tree recursion point, which is here. So we need to steal the same lines. And what we're going to do is have a third model, one which is never used to measure gradients, just used as support points. And each client, the update is that I'm going to compress the difference between my current model and the hat k of, sorry, my current model wk plus 1 and hk, the support point. And each client is going to update his model by adding this compression to hk. This clearly preserves the unbiasedness. And updating hk plus 1 in the same direction, but with a step size that avoids the propagation of the variance. Okay, so again, now what I want you to remember is this idea is that I can actually do stochastic gradient descent with gradients measured at random points. That's actually not going to impact that much the convergence. And I can find a scheme that satisfies those conditions. The technical scheme here, maybe it's, I don't believe I understood that in the first 5 minutes I saw that. So maybe you don't get it right now, but maybe you have the curiosity to look actually how it works. It's interesting. OK, so just something to show that this 3-point scheme is the only one that satisfies, that reduces the variance as we go along the way. All the other schemes that we showed before have variance that explode or increase, and this 3-point scheme actually enables to have the variance that decreases along the way. Okay. So one results, because I think most of us are mathematicians, so we want to see theorems and convergence rates, but this is just, again, mathematical quantification of what I've said before. What I'm going to show is that when I do that, I'm actually able to mathematically remove the impact of this downlink compression. Okay? So what I have is that when I look at my convergence rate, again, I have 2 terms. I'm not going to show everything, it moves a lot. This is slightly different from the theorem before. This time I have choose to state the theorem for decreasing step size, where the step size decreases proportionally to the horizon k, the number of steps I'm going to perform. So these are step size that go to 0. Again, for those experts on stochastic approximation, we would recognize the convergence rates for a smooth function that scales as 1 over square root of k for stochastic gradient descent. And the interesting thing here is that the dominant term that scales as 1 over square root of k is actually not impacted by w down, so omega down, sorry, my compression constant on the downlink compression. So if I ignore second order terms, I actually have a convergence which is exactly the same one as if I didn't have the compression that I performed from the central server to the local workers. Okay, so this algorithm was Cohen's model compression with memory, because we actually compress the difference of the models, but not towards the model that the agents holds, but towards the model which is a memory model, which is never used apart from that support for the difference of the compression. Okay, so again, just a quantification that using feedback loops enable to somehow remove the impact of compression or remove the degradation of compression. So this is really helpful in practice. Okay, skip that. We have extensions. And just one interpretation I want to make. So wait a second, for the moment this doesn't make much sense, but I mentioned the link with what we call the link with randomized smoothing. So what we do in stochastic gradient descent is that. Okay, I take my point, I take a stochastic gradient at that point, and I make an update. And what we are doing right now is something that looks more like that. I take my central point. I have a distribution of models around that central point. I'm going to observe a stochastic gradient at one random point on that circle. I observe that stochastic gradient. And now I apply it to WK, right? So this scheme was known for a while. It's like if you add the noise voluntarily, this is a paper in 2012, I think, Ducci and al., which is actually actively adding noise in order to smooth the functions that you have in optimization, transform non-smooth functions into smooth functions. The only difference here is that we don't actually smooth the functions, and the noise that we suffer from is adversarial. So it's not a noise that I choose, it's a noise that I suffer from. But the fact that those algorithms are going to converge well enough if the variance between WK and W hat k is controlled is something that we knew for a while. Okay, and in practice, that's great. It actually works. I mean, for once, theory matches practice. If I look at the convergence rates of naively doubly compressed algorithms or the new algorithm that I described, and here what Diana, the orange line is algorithms that perform just compression in one direction, we actually find that algorithms that perform double compression here, the purple and the brown one, converge just as well as algorithms performing single compression. But if I do the same thing in terms of number of bits, now obviously I have a much better performance. Okay, so these kind of schemes actually work pretty well in practice. So I can summarize this second section. What we have talked about is mitigating compression with feedback loops. Okay, this is very related to randomized smoothing and this idea that I can keep all the information you send me, apply my updates, and only afterwards send a random model to each of you. Okay, and the proof techniques, again, are not very complicated. It actually relies on defining energy functions that are going to decrease along the way, and that combines my iterate performance with my model variance between my model and the local models, and this kind of things. And we can extend that to having all different models to each on all of you, and that works also very well. How much time do I have right now? I can stop here, or I can give you hints on the last part. I don't remember when I started.
5 minutes.
Oh, this is perfect. 5 minutes before questions, or am I taking time on the questions?
5 minutes before questions.
Okay, this was already a coherent part. Okay, let me just, I was given the authorization to do 5 more minutes, so I'm going to do that. I want to say that I just take one step back and now not talking about algorithms anymore, just design of compression schemes and quantization schemes. What do we want actually for those compression schemes to work? I've said we want unbiasedness. I've not said really why, but I think it's interesting to think back on what people were looking for in the 70s when they were doing like compression and quantization for signal processing, and what we are looking at today in machine learning. And that, I think, 3 differences. The first one is typically in traditional models, like in information theory. I think I heard that in my lectures back in Orsay. I think Elizabeth was teaching that. Am I correct? Yeah. Typically what you try to do is find the best quantization scheme depending on the distribution of the data. And typically you want the error to be very small. And typically you do that and you look at the performance on one point. The things that we're going to do in machine learning is actually we don't really care about 1 point because the point we try to compress is already stochastic and already has noise. So achieving a very small error doesn't really make sense. We have no clue about the distribution because actually no one really understands the distribution of gradients after some training on a deep neural network of crazy size. So no clue about the distribution. We are compressing random points and we are doing that iteratively a lot. Meaning that we are going to do that thousands of times, as many times as iterations, and thousands of times because there are thousands of persons doing that. So we actually really need this unbiasedness property. We actually need that on average we have the correct signal, but it's okay if we have some variance because we are going to reduce the noise effect by averaging a lot along iterations and along clients. Okay, so I think these are like the 3 things that make compression in signal processing, traditionally I would say in machine learning today or distributed learning, somehow different in terms of what we look for. And so this is the assumption that we had before. So I'm just restating this assumption. And what I'm going to just show you afterwards is to show you how we can obtain a scheme based on Voronoi quantization. And maybe I'm not saying it's super useful. I'm saying it's very funny. Okay, so or more or less like that. For the moment, it's not something that is implemented in practice because it has some drawbacks. But it's actually a nice way of constructing a Voronoi scheme. So I'm going to find a set of code words, maybe a grid. I'm going to take the nearest neighbor to my points on that grid, and I want that to be unbiased. And at first, it looks just wrong. I mean, if you do traditional Voronoi quantization, that doesn't work. I have a fixed grid, I take a point, my compression is deterministic. So if I want to have stochasticity in my compression, and I say that my compression is almost surely the nearest neighbor, the only thing that can be random is actually the codebook itself. So this is exactly what we're going to do. We're going to say, I'm going to consider Voronoi quantization on a codebook, which is going to be random, and I'm going to say that I can make that unbiased. So how does that work? This is Voronoi quantization. Okay, I take my point, I take my codebook, which is the green crosses, I take my x, and I send that to the nearest neighbor on the grid. Now, with a random codebook, what happens is that I have this scheme. Let me try to have it. Okay, move it like that. I change the codebook each time. Okay, and each time I change the codebook, I change the point towards which I send x. Okay, now how can that be unbiased? At first, it doesn't seem like it's going to work. There is no reason that the average over the code words distribution of the nearest neighbor would be x. Okay, so that's where we have a small trick. What we're going to say is that we're going to consider a unitary invariant code distribution for the code words. Typically a Gaussian isotropic, or any grid that I would just uniformly rotate before taking compression. That means that the distribution of my code words now is, like unitary invariant by rotation. And now what I'm saying is the following. I'm saying that when I do this compression of my x on this unitary invariant distribution, it has to be aligned in expectation with x. Again, this is just by symmetry. I mean, if I would take x here on the axis and I say my distribution of the code words is unitary invariant, there is absolutely no reason that expectation is on the top or the bottom of the x-axis. So I'm saying that on average, the expectation of my nearest neighbor in a unitary invariant codebook is aligned with x. And I'm saying that this ratio between these red dots and my x points at the beginning is a function that is only depending on the norm of x. Again, same unitary invariant arguments. I'm saying that this function is not explicit. That would be kind of too good to be true. I'm saying that this function is easy to compute because it's just a one-dimensional function, and we're going to apply that in high dimension. So that's the scheme. That's where it stops. If I have a code word distribution which is unitary invariant, then for any number m, there exists a function which is this rescale function, which goes from r plus to r plus, such that the expectation of my Voronoi quantization of x on the codebook, expectation over the distribution of the codebook, which is distribution p, which is unitary invariant, is this scaling rmp times x. So unbiasedness. And now I can exactly use that in my scheme. I can say I do this compression, I sample a codebook, and when I want to transmit information, what I'm going to do is I'm going to sample the codebook on my side, find the nearest neighbor, send the index of the nearest neighbor, and whoever I send the index of the nearest neighbor to is going to sample the same codebook. So this assumes that we're sharing seeds, sampling seeds, and this is an old trick from quantization too. And sample the same codebook, find the nearest neighbor, use that. And I'm also going to send the information R, this like rescale thing. And this information is just one-dimensional, so I can also send that not for free, but for limited cost. And we can actually compute the function, so the function is kind of regular. And I mean, we can have like this kind of like shapes of the functions. This is just numeric. Okay, and this is basically the first 2 pages of these things we have been working on. And then, because we were working with Eric Moulin and Gilles Pages and these kind of guys that are like mathematics a lot, we did a lot of mathematics on those things, trying to actually show that our codebook and the scheme was optimal in some sense, and in higher dimensions, etc., etc. So there is a lot of nice mathematical properties to derive. But I think the idea itself is kind of neat too. And that being said, I think this summarizes the third part and the last part of the talk. We can design compression schemes that are actually efficient in practice also. I haven't mentioned that, but taking this nearest neighbor is actually a very good way of reducing a lot the error that we perform. And in practice, this performs much better than any other scheme that we have with the same number of code words. And plus, we have the flexibility of the number of code words. It's actually a very good scheme. It's just a bit heavy to actually use in practice because of these sampling schemes of the code words, and meaning that if all of you have sampled a different code book, find the index, you all send me the information, I need to sample like now 40 code books on the central server. So not saying it's meant to be the most practical, but in terms of compression error, it's actually very efficient and typically does 4 times better than compared schemes at least. Okay, and the properties that we want to satisfy, something I think is interesting when we think about compression in distributed settings. And afterwards, there is a lot of mathematics to do, but I don't want to get into that. And yeah, this is just the main slide of the conclusions. Thank you very much, should be written here. And we have 3 parts that I hope you can remember about. The interaction between heterogeneity and compression, and this effect that without correction, I'm going to be diverging even if I have gradient descent and partial participation. The randomized smoothing and error feedback loop ID, and the quantization with a Gaussian codebook ID. And these 3 things correspond to 3 kind of independent things about federated learning and compression. Thank you very much.
Thank you, Aymeric. So do we have questions?
Yes.
Sometimes in practice, methods of variance reduction are not very effective, but you are saying that in your case, this is pretty good.
Okay, so this is an excellent question. So for those who know variance reduction, there's something nice about variance reduction is that in the convex regime, it's kind of the state-of-the-art method. So if you do logistic regression, you have very large n, and you use scikit-learn. you look at the documentation of scikit-learn, I mean, they say that one of the best methods is SAG or SVRG, those variance root methods. This converges very well. Basically, it has nearly the same convergence property of the gradient descent, but with the complexity of stochastic gradient descent. So in the convex regime, it's excellent. In the deep learning regime, it's a bit unfortunate because SAG, SVRG, they have been around for 10 years. They're like super well cited, super well organized. It's not that people don't know about those methods. They are not even implemented in Keras or PyTorch. They are not even suggested optimizers. And the reason for that is that, I mean, if you use those variance reduced methods, typically you don't get a good performance. Okay, and understanding that requires understanding optimization for deep learning on very non-convex landscapes. And the best explanation I can come up with, which is already not something I'm sure about, and it's not my explanation, is saying that in some sense those deterministic or semi-deterministic methods end up into points that have poorer generalization performance than points that have more stochasticity. So it's actually saying when I do optimization in deep learning, I require to have at least some amount of noise, and reducing too much that amount of noise is going to degrade the optimization process. That's also where, I mean, this is the answer. But that's also where, in some sense, whatever we do in convex and stochastic optimization is in some sense limited. All the rates that I showed you, I mean, would actually improve when I reduce the variance. That's why I showed rates in the convex case, because I believe that those rates are meaningful. But I can also give rates in non-convex regimes, which are convergence rates towards critical points. But I do not believe that those rates actually really reflect what happens in deep learning. These are rates for non-convex optimizations. But generalization in deep learning is something much more complex, and that's not fully understood yet by anyone. Sorry for the long answer. Yes?
Are you interested in mitigating one malicious client and like that would send some too big gradients to the server? So the question is also like, so sometimes when you have this kind of setup, you would like to take the median instead of the mean. And does your analysis, like, are there some interesting stuff with compression to resist, to be resilient to attacks?
Okay, two answers to that. So first, the framework of being robust to adversaries is something I should even have mentioned at slide number 2. I think maybe it was on the slide, but here, one of the challenges that we may face is adversaries, in the sense that some of those clients, Sylvain again, probably, is sending us malicious updates. So he's trying to fool us into having a very bad generative model for text, for some reason. And so we want to avoid that. And one classical way of avoiding the bad influence of one point in a distributed system is, as you said, medians. Instead of taking the average of all the opinions I receive, I take the median, yet to be defined in high dimension. In dimension 1, we know what the median is. There are several ways of defining the median in high dimension. If I do that, I'm actually going to be robust to some part of adversaries. So this is a very important direction. The question now is, what are the interactions between compression and adversaries? And the answer is I haven't seen that done in practice. May have missed it, though. And the one direction that could help is a bit the same as for privacy. If I do compression by reducing the number of information that I send by sending only a few coordinates, now have a lower dimensional system, which helps me if I want to add privacy, because privacy is typically not very good with dimensionality. And same, maybe some schemes that we use for adversaries can be easily implemented in lower dimension. So that would be the answer. But I haven't seen quantization and adversaries together and the relationship between the two.
No other questions, so thank you, Aymeric.
Thank you.